Hello, hi everyone. So in the last class we were discussing this first order logic, and these three questions I gave you as a homework. Did you try? Any doubt? Did you try these questions? Let me know. Naim, did you try these questions? Okay, so let's see their solution. In this question, okay, the first question, let's see. For all x, for all y, there exists z psi, and a model of size 3 is given. So let's see. For all x, for all y, there exists z and some psi. Now, this is a formula. This is a first order logic formula, and for this formula, he is saying that there exists a model. There exists a model of size 3. Let's assume this is given. Basically, he is saying that there exists an environment in which domain has size 3. Basically, we have there are 3 elements in the domain, and for that domain we have some interpretation of this psi such that this is basically this g is becoming true. This is given. Now what he is asking, he is asking, can you guarantee that there is a model of size 2? This is the question. Can we guarantee that model of size 2 will be there? Let's see. This is the question. Okay, now again, what you can do, you can just take 3 elements. So he is saying that there exists a model of size 3. Let's assume this is the domain A, B, C. Now, and he is saying that for all x, for all y, there exists z. Means like this: A, B, C, A, B, C, and A, B, C. So for all x, for all y, there exists z. Means it's like this. From here you can take all the possible pairs. Like here you can take any a comma b comma c. Here also you can take any a comma b comma c. And for each of these pairs, there exists someone. Maybe for a comma a there exists b. So like this. Okay, for every pair there exists someone. And now he is asking, can we guarantee a model of size 2? Let's see. The point is, can we guarantee a model of size 2? Let's consider this a comma b. What we will try to do, we will try that there does not exist a model of size 2. That is what we will try. Okay, now if we succeed, then we can say that of course we cannot guarantee. So can we succeed? That is the point. So let's take this scenario. Let's assume that a b c, and let's assume it's like this. Let's assume that for a comma a there exists b. Let's assume, and for a comma b there exists c. It's like this. We are taking this. For a comma b there exists c. Okay, and for a comma c there exists b. What we are doing? We are doing like this. For a comma a there exists b. For a comma b there exists c. For a comma c there exists b. Something like this we are doing. For b comma c there exists a. Something like this we are doing, because for every pair there exists someone. Okay, now if we take this a comma b, okay, if we take this a comma b, then can we for this a comma, for this domain, let's check for all x, for all y, there exists z. Now for this domain we will check a b here, and a b here. So for every pair here there must exist someone. But you can see for a comma b there does not exist anyone, because you can see for a comma b there was c, but for a comma b there does not exist anyone here. So you can see if we take a comma b, this domain if we take, then we will not succeed. You can see, because if we take this domain a comma b, then this will not become true. You can see, because for a comma b no one is there. You can see for a comma b actually c was there in previously. In this given scenario, for a comma b we have c, but in this we have no one for a comma b. So that is the point. Now you can take b comma c also, does not matter, because in this scenario for b comma c we have a. Now what we have here for b comma c. Like if we take b from here, c from here, then who is there for b comma c? No one is there. So you can see we cannot guarantee a model of size 2. Is this clear? We cannot guarantee a model of size 2 here. If similarly, we cannot guarantee a model of size 1 also. You can very easily see, because you can see for a comma a there is b. For you can see for a comma a there is b. For b comma b, let's assume there is a, and for c comma c, let's assume there is a. So you can see we cannot guarantee a model of size 1 also. If you take a, then you can see for this a comma a, who is there? For a comma a, b is there, but here we do not have b. So that's why you can say that we cannot guarantee model of size 2, we cannot guarantee model of size 1. So in this question, how will the third set be mapped to other two set? When we point b to c, is it for every possible pair? So let's see whether I can answer your doubt or not. See this scenario. Okay, let me give you some diagrams I am going to give you. This yesterday also we were talking about this. There exists x, there exists y psi. It means what it means? It means that there exists someone here, there exists someone here, such that for this pair, let's assume there exists someone here, there exists someone here, such that for this pair psi must be true. Psi true. This is the meaning of this there exists x, there exists y. Now if you see there exists x for all y, let's see this. What is the meaning of this? So again, this is the domain of x, this is the domain of y. Then this says that there exists someone, at least one, such that with him you can take everyone, with it you can take everyone. And for all these pairs, means for all these pairs where this is a and you can take everyone here, everyone from y, you can take basically complete y, you can put here. For this type of, for all these pairs, psi must be true. This is the meaning of there exists x for all y. Means there exists someone here, with it you should be able to take everyone, such that for these pairs psi is true. Now let's see what is the meaning of for all x there exists y psi. What is the meaning of this? For all x there exists y psi. Let's assume again the domain of x is this, domain of y is this, and this is psi. Now this is saying that for everyone there is someone. For everyone there is someone. Okay. For example, like if you have a comma b comma c, then for a you can have someone. For b also you have someone. For c also you have someone. For everyone you have someone. For everyone there is someone. Okay. So are you getting this point? Here we are saying that there is someone who is for everyone. There is someone, like there is God for everyone. So there is a fixed person who is for everyone, like God is for everyone maybe. Similarly, here he is saying that for everyone there is someone, like for every man there is a mother. So for everyone there is for every man there is a mother, like this. So you can see. So that is the difference between here. Here we have someone, some fixed person, at least one person for whom everyone. And here we are saying that for everyone someone, for everyone there is someone. They can be same, they can be different, we do not care, but for everyone there must be someone. This is the meaning of for all x there exists y. Now if this is clear, you can and what is the meaning of for all x for all y? The meaning again, this is very simple. This is saying that for everyone, like for everyone, it's like a complete bipartite graph. This is basically a complete bipartite graph, you can see, because for everyone. Okay. Now this is the meaning of for all x for all y psi. Now you can also see if you have three quantifiers. Let's assume you have there for all x there exists y for all z. Now you can draw the diagram also here here also. For example, this is, let's assume a comma b. Let's assume this is 1 comma 2. Let's assume this is p comma q. Then basically this says that for everyone, means for everyone there is someone. Now for everyone it's like this, like for everyone, for a there is someone from here, let's assume that is 2. So for a there is 2 from here. Now you take everyone here, means p also, means q also. It's like this. For this, psi must be true. Also remember, for everyone, so for B also there is someone, for B also there is someone, for B1, and now for everyone, now P you can take, now Q you can take. So for this, psi must be true, like this. Is it clear, Naim? Let me know. So like this you can make the diagram. Okay, you can make any number of quantifiers you can take, does not matter. For example, let me take more quantifiers. There exist X for all Y, there exist Z for all P psi. Let's assume you have this scenario. Then how it will behave? Very easily you can see. Let's assume this is A comma P, this is 1 comma 2, this is P comma Q. Let's assume this is something X comma Y. Now how it will behave? It will behave like this. He is saying there exists someone for everyone, like there exists someone here, there exists someone, maybe A. Now he is saying for everyone means with A you have to take everyone, with A you have to take everyone here. Now for this, now this pair is there. For this someone, maybe for A comma 1 maybe you can have Q, maybe for A comma 1 you can have Q, maybe for A comma 2 you have P. Are you getting this point? Basically for this someone means for this someone means similarly for this someone. Okay, after that for this, now after that for this everyone, now everyone means you should take X also, you should take Y also, like here. Similarly here for this everyone means X also, Y also. Of course these two things, like there will be four things. One is A1 QY, one is A1 QX, one is A2 PX, and one is A2 PY. So for these pairs psi must be true. Then for B1 here we can have P also here. For B are you talking about this example? Are you talking about this example or previous? Which example? 9. You are saying then for B comma 1 here we can take P also. Like here he is saying that there exists someone. So that person can be A also, that person can be B also. There exists someone. Okay, so maybe that is A, there exist. So you can take from here A. We are guaranteed to have at least someone, so you can have A here. Okay, for that person now you take everyone from here, means you take everyone from here. Okay, now for these pairs there is someone here, so for example for this pair there can be P, for this pair there can be P also, Q also, there can be P also, Q also, maybe P. Let's take P, does not matter, you can take Q also. Now for this triple, for okay, this is for all, so for this triple now everyone. Okay, so like this. Now for this triple now you take everyone, you take X also, you take Y also, both, like this. This is how you can play with these quantifiers. Very easy, nothing hard here. Now let's come back to our question. So this was our question here. We have done it. So we cannot guarantee a model of size 2. We cannot guarantee a model of size 1. Okay. Now let's see more. And for this question, can we guarantee a model of size 4? Let's see. So for all X, for all Y, there exists Z. This is our question. And for this, it is already given that there is a model of size 3. Now, can we guarantee a model of size 4? Did you try it? Can we guarantee a model of size 4? Tell me. Can we guarantee this? So if you see, so if you have you can see, actually you can very easily you can see it. So if you have A comma B comma C, here he is saying that for everyone means for every pair there is someone, for every pair there is someone. So can we have a model of size 4. Can we have a model of size 4? Yes, we cannot guarantee. Very easily you can see we cannot guarantee. Why? Because if you assume model, if even if you take this ABCD, even if you take this, then also what he's saying, see, this will guarantee, what it will give you guarantee, it will give you guarantee that for every pair, like if you take a comma b, if you take a comma a, whatever pair you take, a comma c, b comma a, whatever pair you take, for every pair you have someone. For a comma b you can have c, for a comma a you can have c, for a comma c you can have b, for b comma a you can have c. For every pair there is someone. This is the guarantee. This is given information. This is given. Now from this given information, can you guarantee that there will be a model of size 4? Let's take this. Let's assume. Let's take this. Now you can see that this statement is saying that for all x, for all y, there exists z. Now here we have a, b, c, d. Here we have a, b, c, d. And here we have a, b, c, d. Now again, this is saying that for everyone means, but the point is, who is there for d? Who is there for d? Maybe there is no one for d. Okay, maybe there is no one for d. So that's why you can see that we cannot guarantee a model of size 4, because who is there for d? So that's the reason. This is how you can solve it. So this is a template. This is a kind of template if you see. Okay, what is this template? Like in yesterday's class we have seen one type of template. With the practice you can make these templates. Like in yesterday's class we have seen this template, there exists x, basically a sequence of there exist, then a sequence of for all. This was a template, if you remember. A sequence of there exist, then a sequence of for all. For this template we have seen some results. Whatever you do, you take, whether you take this or whether you take this, okay, whatever you do like this, you can see that for this template, if it is given, let me write, I told you tomorrow also, yesterday also I told you that for this type of template, let's assume that there are, let's take this template, there exists x, there exists. Let's assume there are there are n there exist, and then there are m for all. Let's assume that n comma m both are greater than 0. Means this template you have. Now for this template I told you that if it is given, let's assume if it is given, if given a model of size greater than or equal to n. If it is given that there is a model of size greater than or equal to n means these there exist. So if it is given, then you can guarantee, we can guarantee a model of then model of size n we can guarantee. This we can guarantee, model of size n, because of these there exist. Okay, this template we have seen yesterday, if you remember. I took two examples. Okay, one example was single there exist. Like this was one example that we had taken. There exist x for all y shy. This example we had taken. Then we had taken this example, there exist x, there exist y for all z. So this we had solved, and I told you you can solve many other questions. You can take 3 there exist, 2 for all, and all these things you can do. So if you remember, this we have done, this we have done. If you have any doubt, you can just watch yesterday's lecture. There I have already done it. So this will tell you this result you can make. That if it is given that model of size n is there, see from where this n is coming, because of these there exist. In this template, everything is controlled by these there exist. Everything is controlled by them. Okay, so now if it is given that there is a model of size greater than or equal to n, maybe it is given that a model of size n plus 1, then also you can guarantee a model of size n, you can definitely guarantee, but it should be given, then you can guarantee this. Okay, now yeah, but remember, we cannot guarantee a model of size n minus 1. No, that we cannot guarantee. Like we can say that model of size model of size less than n, this we cannot guarantee. So anyone has any doubt in this template, let me know. Do you have any doubt in this template? If you have any doubt, I can take an example. I can take one example and I can explain it again why this is happening. Anyone has any doubt in this template? Let me know. This is actually your GATE 2017 template. Okay, so let's see the GATE 2017 question. Here you have your GATE 2017 question. This is your GATE. Okay, sorry. Yeah. So this is the GATE 2017 question. You can see. Here he is giving there exists x, there exists s, there exists t, there exists u, then for all. So there are basically 3 there exist and 4 for all. Like this is given to you in the question. Okay, so I think I can do it. So in the GATE question, what they have done? They have done this in the GATE question. In GATE 2017 question, this is the question. There exist, then for all. This is given. And for this they are saying that there is a model of size 7. This is given to you. They are saying that there is a model of size 7. Now they are asking, let's call it G. Now they are asking, options are there. Now I told you for this template, we have already seen this template, and I told you that if there exists a model of size greater than equal to 3, I told you, if there, because there are three there exist, then there are 4 for all. If it is given that there exists a model of size greater than equal to 3, yes, it is given, model of size 7 is given, then you can guarantee model of size 3. Model of size 3 you can guarantee. Okay, this you can guarantee. Actually, model of size 3 also you can guarantee. Model of size 4 also you can guarantee. Model of size 5 also you can guarantee. Basically, between 3 and 7 you can guarantee everything. 4 also you can guarantee. 5 also you can guarantee. I will prove it, don't worry, I will prove it, that you can guarantee a model of size 4, 5, all these things you can guarantee. So, but you cannot guarantee a model of size 2. So anyway, now if you see the options, let's see the options. These are, let's see. Now, the first option is saying, there exists at least one model with universe of size less than or equal to 3. This is correct. Because of this or equal to, this is correct. Because we can guarantee at least one model of size 3. Size 3 model we can definitely guarantee. If this or equal, if this is not there, if this equal is not there, then this option would not be correct. Now the option second is saying, there exists no model with universe of size less than 3. This we cannot say. See, we cannot guarantee that there is no model. The point is that we can say there may or may not exist. We cannot guarantee the existence, but this does not mean that we can guarantee that there is no model. So this statement is false. Next is saying, there exists no model. Again, this is also not correct, because this also we cannot say. Now next is saying, every model is of size equal to 7. This is also not correct, because you know that size 3 model is guaranteed. So the answer will be option A. This is a very nice, this is a very easy question. Now let me tell you few things. Actually, this is 2017 question, and in that year when 2018 question. This is a 2018 question, and in that year when I was preparing, I also appeared in GATE 2018. In that year my rank was 67. So you can see this question I did correctly. Okay, I read this question, and at that time I did not have this much this much understanding of this model concept. I did not have, but I read the complete question, and I thought about it like this. I took a small example. When I saw this template, I actually took a small example right at that moment. I took like this, there exists x for all y, like that I took example, and I just I analyzed it, and I marked it A. So you can see like this. So in the GATE exam, sometimes what will happen, a brand new question can be, can come in maybe in GATE 2021. There is a question, let's assume there is a question which is brand new, like you have never seen this type of question. Then also you can solve it. Like, it's not that you cannot solve. Then also you can, you at that moment you should try to think. Maybe you should try to understand this question. Maybe you can take small example and you can try. But the point is that you can try it, and many times if you have a good understanding, If you have a good analytical ability, then you will be able to solve it. Sometimes, maybe sometimes do not, but anyway. Now the point is, I was telling you that we can guarantee a model of size 4 also. So why I was telling you this? Let's see. Consider this, there exists x, there exists y. Consider this small example, 4 all z, 4 all m. Let's consider this example. This is your g. Okay. Now for this, assume that they give you a model of size 4. Let's assume given model of size 4. Let's assume this is given to you. Now let me check, can I guarantee a model of size 3? Model of size 3 I want to see. Can I guarantee a model of size 3? Yes, I can guarantee. Why? See, this is given information that there is a model of size 4, A, B, C, D. Let's assume these are the elements A, B, C, D. Okay. If this is the A, B, C, D, then this is saying that there exists someone, maybe A. Again, there exists someone, maybe D. So A, D. Now with A, D, you take everyone, like you can take everyone, you can take all of them, A, B, C, D. You can take everyone, A, B, C, D. So can you see? This is the given information. So far, I have just used the given information. This is the given information. There exists someone. So A, D. Now you can take everyone from here, does not matter. Okay. Now for these things, psi is true. This is given to you. Psi is true. This is given. Now let's see, can we guarantee a model of size 3? Let me know. Can we guarantee a model of size 3? Let me know. What do you think? Can we guarantee a model of size 3? You can see, yes, we can guarantee a model of size 3 because just directly take this AD and take this B. Just directly take this ADB. Take this. Yeah, see, I am taking this AD and then I am taking just one more element B, ADB. Now you can see for this ADB, there exists X, there exists Y, for all Z, for all M, psi. You can see there exists, again, this is my ABD. This is ABD, this is also ABD, this is also ABD, and this is also ABD. Now you can see, you can very easily see that with there exists someone, so yes, A is there exists someone, yes, D is there, and now with them you can take ABCD, so you can take ABD, so you can see I can guarantee a model of size 3. Model of size 3 is guaranteed. Similarly, you can guarantee a model of size 2 also. You just take A, D. Just take these. So you can guarantee a model of size 2 also. Just take this. But you cannot guarantee a model of size 1. For example, if you take A, you cannot guarantee a model of size 1. Why? Because who is there for A? There exists someone, yes, A. Now who is there? With A you cannot take A because you can see here with A you have D, with A you do not have A. So that's why you can guarantee model of size 3, you can guarantee model of size 2, but you cannot guarantee model of size 1. Okay, so this is the point. Okay, now let me ask you one more question. Can you guarantee a model of size 5? Model of size 4 is given. Now can you guarantee model of size 5? For this formula, let's assume given है model of size 3. Let's assume so model of size 4 is given. Can you guarantee model of size 5? Can you guarantee this model of size 5? Let me know. Think about it. Can we guarantee this? Yes, we cannot guarantee. See, why we cannot guarantee? Again, the same thing. Just take A, B, C, D. Now you know there exists someone, maybe A. There exists someone, maybe D. So with this A, D, with this A, D, you can take anyone here. But remember, anyone means ABCD. Anyone means ABCD. By anyone I mean ABCD. Now let's take model of size 5. Assume that I take all these things, A, B, C, D I take, and additional element I take E. Additional element I take. Okay. This additional element I take. Now you can see that there exists X, there exists Y for all Z, for all M psi. Now you can see that, of course, there exists someone, yes, A. Okay. There exists someone, yes, B. Now for all means A, B, C, D, E. But remember, this A comma D, yes, they can go with A, they can go with B, they can go with C, they can go with B, but they may not go with E. Are you getting this point? Because here what we have guarantee that with this AD we can take anyone from these four. So yes, we can take any one of these four, but what about E? So that's the reason we cannot guarantee a model of size 5. So this is how you can solve all these model questions. These are very interesting problems. Okay, I hope that you are getting some some interest in these problems. Very interesting, analytical. Like if you have some random question, then you need to analyze that question. So this is a nice type of problems that we have. So this question we have done. Now I hope that you have done this question also. You can answer it. This is okay. Yeah, this we have already done. This is just now we have done this just now. So if we have a model of size 3, then you can very easily you can check it. Okay, so this we have done, this we have done, and this you can just take it as a homework. Okay, this is similar to this question number 1 and question number 3, both are same template is same. Here also a sequence of for all, a sequence of there exist. Here also a sequence of for all, sequence of there exist. Template is same. So you can solve this question 1 we have done. Automatically you can do question number 3. So these homework questions we have done. Anyone has any doubt, then you can ask. So this is all about this model concept. Very interesting concept actually. So if okay, this is over. Let me know if anyone has any doubt. Any doubt in the propositional logic or first order logic, whatever you want me to teach, I will teach you. Right? We have 20 minutes. If there is any topic you want me to teach, I will teach you. In first order logic or in propositional logic, any topic that you want. Let me know. Let's see this GATE question. This is also a GATE question, 1991. This is also, you can very easily solve it. He is asking, does it have a finite model? Is it satisfiable? So this question is also interesting. Okay, so GATE previous year questions. So drinker's paradox, yes. Okay, that is a nice problem. Yes, drinker's paradox. That is a nice question. So that will tell you some things about this. Let me take drinker's paradox. We will take. So many things we have done, and now we will take drinker's paradox. So let's see. There is something called drinker's paradox actually. This is a nice problem in first order logic. What is this? Let me tell you. I am giving you a statement. You just think about this statement. Don't worry about mathematics. Don't worry about first order logic. Okay, just forget about all these things and just think about this statement. Right now, there are 8 students here in this live class, including me. Okay, and I am making a statement. I am making a statement that there exists someone here. This is my statement. See, this is my statement. There is someone here. In this live class right now, I can see there are total 8 students. So there is someone here such that if he or she is a drinker, bevda, whatever. So there is someone here such that if he or she is drinker, then everyone is drinker. This is the statement. Think about it. Does this statement make any sense? If I ask you what is the truth value of this statement, is it true? Is it false? It is always true. Is it sometimes true, sometimes false? or is it always false? Like, what can you say about this statement? Just think about it like a normal person. Don't worry about discrete mathematics, don't worry about first order logic, mathematical logic. Just think about it. What do you think of, what do you think this statement that I have in front of you, is it always true? Is it always false? Is it sometimes true, sometimes false? What can we say about it? Let me give you another question also, so you can think about it. Basically, I'm saying that there is someone here such that if he or she is drinker, then everyone is drinker. Everyone. So similarly, you can make this type of statements. Many this type of statement you can make. Actually, on Wikipedia, if you find there is a statement, I don't want to write this statement, but this is also a famous statement. That's why I am writing it. So there is this statement that there exists a woman in this world. There is some woman in this world. In this world, such that if she is sterile, she is infertile, or what, let's call it, she is infertile. If she is infertile, then world will end. Now this statement, he's saying this on Wikipedia. You can find this statement, but anyway, this statement is saying that there is some woman in the world such that if she is infertile, means she cannot she cannot give birth to child, then world will end. Now does this statement make any sense? Is it making any sense to you? Like, is it true, is it false, is it always true, always false? What can we say about it? So actually this is also true, and the previous statement is also true, and these are always true. Does not matter, these are always true. Now we will see, I will give you the proof of it. Let's see, I will give you proof. You will see that this statement is always true, always. This is actually tautology. This statement is a tautology. Does not matter, this does not matter on number of people, like I am saying here. Okay, yes, that's why I feminist loading, so that's why I created some preface. I gave that this is from Wikipedia, this is not my statement. Now anyway, let's see. So let's focus on this statement. What is this saying? This is saying that there is someone here. Let's assume here, by here I mean, let's assume there is a domain, and in this domain you have some elements. Let's assume, by here I mean domain. Okay, now some domain, some values are there, some elements are there. Now we are saying that there is someone in this domain, such that if he or she is drinker, then everyone in this domain is drinker. First we will rewrite it, this statement, in first order logic. How are we going to do it? So you can do it one by one. So first he is saying that there is someone here. What it means? It means there exists someone, there exists X, such that, okay, there is someone here means there exists someone, there exists X in this domain, such that now this is given. If he or she is drinker, okay, let's assume that this domain is let's call this domain N. This is your domain, let's assume. Now if he or she is drinker, means d of X means X is drinker, implies everyone is drinker, means for all X dx. This is how we can convert this given statement, we can convert into first order logic formula. Is this okay? Did you get it? Very easy. See, he's saying there is someone here. Yes, there exists X in this domain. This domain is N. Okay, there is someone here such that if he or she is drinker, if then, this is basically if then statement. So this implies this, means he or she is drinker, means X is drinker, then this implies for all X they are drinker, everyone is drinker for all X dx. So this given statement I have converted into first order logic. Now what I am going to do, I am going to analyze this statement. Only this statement I will analyze. Let me analyze it. So the statement that I have is there exists X such that if X is drinker, then for everyone that is drinker. Remember, this X has nothing to do with this X. Okay, you can write y also, does not matter. I told you this x has nothing to do with this x. You can write y also. Basically, for everyone that is drinker, for all y dy. If x is drinker, then everyone is drinker for all y dy, like this. Okay, and this is the domain set of, this is our domain. Now I am going to take two cases. Case 1, assume that in this domain everyone is drinker. Assume everyone is drinker. Already assume everyone. Assume in an everyone is drinker. This is the first case I am taking. So in this case, this is very easy, because of course, if everyone is already drinker, then this statement is true, because you can see what we can say, there exists x. So you can take any element you can take. Let's assume this a you can take, and for this a, this dA is true, and also this is also true because everyone is drinker. This is the case I am taking. Assume in a everyone is drinker. In this case, you can see this formula. Let me call this formula G. In this formula is true. In this case. Now, what is the second case that is possible? What is the second? In the first case, I am assuming that everyone is drinker. So in the second case, at least one person is not drinker. At least one person is not drinker. At least one person, Z, is not drinker. At least one person, Z, is not drinker. This is the case. Now, in this case, also G is true. Because of Z, this G is true. Because what he's saying there exists X in this domain. In this domain, we have Z. This Z is also present here. In this domain, he is also sitting here. Okay. Now you can see, because of this Z, this internal thing will become true. You can see, because of this Z. Why? Because if you see for this Z, this dz will become false. This will become false, dz, because he is not drinker. So this dz will become false. Now, if this becomes false, then does not matter what is here. This implication will become true. Because in the implication, you already know, if you have P implies Q, if this is false, if this P is false, then automatically this complete thing will become true. So that's why this complete thing will become true. This internal thing, this will become true. Because of this Z. Okay, and hence you can see there exists element. Yes, there exists element. You can just take Z. Because of Z, this internal thing is true. So yes, this G is true. In this case also G is true. So what you can see? You can see that case 1 also, case 2 also G is true. Even if everyone is drinker, then also G is true. If at least one person is not drinker, at least one person is not drinker, Sorry. If at least one person is not drinker, in that case also G is true. So G is always true. So this statement is actually always true. This statement, there is someone here such that if he or she is a drinker, then everyone is drinker. This statement is always true. Is this point clear? Let me know. This is an interesting thing actually. Why is it happening? Let me tell you. Why it does not make any sense to normal people and why it makes sense to discrete mathematics people. Let me tell you. Because a normal people, if you give this statement to any normal person, let's assume who does not know discrete mathematics, if you give this statement that there is someone in the world, there is someone in the world such that if he or she is drinker, then everyone is drinker. Sir, in case 2, why can't we take who is a drinker as Z? See, okay, see here, I have made two cases. The first case is assume that everyone is drinker. This is the first case, okay? And the second case is, of course, in the first case, everyone is drinker. So in the second case, at least one person is not drinker. At least one person. Okay. In this case 2, there is at least one person in the domain who is not a drinker. I am calling that person Z. Of course, there can be more than one person. I don't care. Maybe no one is drinker. But the point is that there is at least one person who is not drinker. Okay. So I am taking that person who is not drinker. Okay. Now, because of that person, this G will become true. Remember one thing. This is the there exists statement. This is a there exist statement, means we just want at least one element for whom this internal thing will become true. We want at least one element for whom this internal thing will become true. So because this, for this non-drinker person, for this Z, this internal thing is becoming true, so this there exist will become true, so this Z will be, so this G will become true. So is it clear, H Sukla? Let me know. Is it clear? See, this is the there exist statement. We just want at least one element for whom this internal thing will be true. We want to find someone for whom this internal thing will become true, and we have found it. Just focus on the non-drinker person. For that non-drinker person, this internal thing will be true, and we just want to find only at least one person, and we found it. Yes, of course, this is the there exist statement. So there exist statement will become true if there exists at least one element for whom internal thing becomes true. Now why? Now actually I just want to give you some idea why this statement is not making sense to a normal person and why it is making sense to first order logic. You can see, you can try this statement. You go and tell anyone that there is someone in the world such that if he or she is drinker, then everyone in the world is drinker. You just tell this statement to anyone, they will think you are dumb, which you are not, but they will think you are dumb. Why they will think you are dumb? Because here they will focus on, as soon as you will say this statement, their focus will automatically go to a person who is drinker. As soon as I will tell this statement to anyone, automatically their focus will go on someone who is drinker. Automatically they will think of Ravi Shastri. Okay, now they will think like this, okay, he is a drinker, but I am not a drinker, so of course not everyone is drinker, so this statement is false. This is how they will think. But a first order logic person who knows first order logic, how he will think? He will think like this. There is someone, basically only existence. We only want existence of someone for whom this thing becomes true. This thing becomes true. So the first order logic person will try to find someone, at least one element for whom this thing will become true. So that is the reason actually. And now what is happening here? Okay, like if you have seen a movie, there is a movie Lakshay. Okay, this is my favorite example actually. Many times, many students I have told this example. If you have seen this movie Lakshay, so in this movie there is a last scene where this is a you can see. So this is a Tiger Hill. Okay, here there is army here. So it's like this. So there is a Pakistani army here. Okay, and they are basically attacking in this side. Okay, and there is Indian army here. So now what they are doing, this mountain, okay, whatever is this is like this. So this is a very like, it is nearly impossible to climb here. That is the point. It is nearly impossible. It's like a straight you can say slope. There is no slope here, basically. You can see like this. Okay, now this Pakistani army, what they this Indian army, what it does, it is attacking from here, this side. So Indian army is attacking from this side continuously. Attack is going on. So now because the attack is going on from this side, so this army is continuously looking at this side. You can see what they are doing. They are doing this, that they are looking at where Indian army want them to look at. Are you getting this point? This in Pakistani army, this is looking in the direction in which direction this Indian army want them to look. But what happens? This Hrithik Roshan goes from this side, and Hrithik Roshan and his team, they climb from this side and they kill them. So you can see sometimes what happens, the things that you are looking at, maybe those things you should, those are misleading. For example, here in this example, if you focus on drinker person, then you will get the answer wrong. If you focus on the drinker, actually you should focus on the non-drinker. But as soon as you will speak this statement, as soon as you will tell this statement to anyone, they will immediately they will think of a drinker. They will not think about any non-drinker. So that is the, you can see, this type of situation is happening here. Sometimes you should think in other direction. There is some Indian player or Australia tour says that he is injured, then whole squad is injured. Yes sir, yes true हो गया लगभग. Yes, so this type of statement are actually always true. What type of statement? This type of statement. There exists x, some property px implies for everyone that property. This statement is a very popular statement, and this G is tautology. This is always true. This is a tautology. This is valid statement. G is valid. Yesterday we were talking about valid, satisfiable, these things we were talking about. You can take this example there. This, remember, there exists x, some property px implies there exists y, for all y py. This G is always true. Basically this G is valid, means there is no co-model. For this G there does not exist a co-model. Okay, now here actually you can see this statement. So any statement which you can write like this, that is always true. So this drinker paradox, like we have seen, okay, or you can see this. You can see this example. There is some woman in the world such that if she is infertile, then world will end. This is also true. Why? Because again this is the same because this is the same scenario. World will end means, of course, if no one gets born, then of course the world will end. But the point is that this is also the same scenario. Now actually this drinker paradox, I found it in a book. Even though you can find it on Wikipedia, but I found it in a book, and the name of that book is, what is the name of this book? This is the name of the book. What is the name of this book? So there is this book. Okay, this book is by some Raymond Samuel. Some Raymond Samuel is there, I think. So this book is by this person, and this person was a great logician. Mathematical logic that we study. So this person was a great logician. He wrote many books, and one of his book is the name of the book is this. You can download it on internet, you can find it. What is the name of this book? This is the name of the book, and in this book you will see puzzles are there. Many puzzles are there, but all the puzzles are mathematical puzzles. Like these puzzles are not like the puzzles that you study in that you read in newspaper. Okay, चार अक्षर का मेरा नाम उल्टा सुल्टा एक समान. These are not those puzzles. These are basically mathematical puzzles. Okay, you need to apply your mathematical knowledge to solve these puzzles. These are interesting, and in this book I found this drinker paradox. So this statement was given: there is someone in the world such that if he or she is a drinker, then everyone is drinker. So this statement was in this book. Okay, so from that book actually you can, if you are good at mathematical logic, if you are good at propositional logic or first order logic, then you should give it try. This book is very interesting. I tried to solve many questions, but of course some of those questions, some of those puzzles I tried to solve. Some I could solve and some I could not, but you can try it. Okay, so this is about anyway, this example is also telling you something about this propositional logic, first order logic. So this formula. Actually, I hope that someday this formula is asked in GATE exam, because this is a very popular. You can see all these type of statements are always true. Whatever you speak, there is someone here says that if he get AIR1, then everyone will get AIR1. So you can see many statements you can make. Okay, infinite number of statements you can make. Okay, which will not make any sense, but they are always true. So this is the beauty of this formula. These statements will not make any sense to anyone, but still these statements are always true.